just take us through the first part of our presentation, just to talk through some of the foundational principles in terms of what statistics are. And here we've got a definition of what statistics are, or what statistics is, the field of statistics is. And it's a mathematics of collection, organization, interpretation of numerical data, especially the analysis of population characteristics, characteristics by inference from sampling. And there are words that are underlined there, which really highlight the process of the research process in terms of data collection, how you organize data, how you manage data, how you interpret data. And we're really talking about numerical data and what, and their methods of converting non-numerical data to, into a format that allows you to apply statistics. And also this highlights the important fact that you're trying to make statements about a population, but you're using a sample. So we're gonna be dealing with some of those factors. Now, the interest really is about how to make sense of numbers. You may be interested in, for example, finding out what is an average salary of workers in a particular company, company A or company B. Or you may be interested in finding out what is the average age of patients presenting with a particular condition in a hospital or at a hospital. Or you may be interested to finding out what is the proportion of children that are likely to die before the age of 5 years in a particular environment. So you're really interested in finding out a particular estimate in a particular population. And you may also be interested in exploring relationships between two or more characteristics or variables of the sample units. For example, you want to find out, you may be interested in finding out, is there a difference in the salaries of men and women in a particular company? So here already you're introducing an additional variable, you're introducing gender as a second variable in addition to salaries. So you're comparing salaries by gender. And you want to see, is there a difference? Or you may be interested to find out if patients with pre-existing conditions compared to those with no pre-existing conditions are more prone to severe COVID symptoms. And this is something that is very topical at this moment as we've been going through this COVID pandemic. So these are some of the questions that you may be interested in asking in performing your statistical analysis. And one of the most important things is you need to understand that the process of making the decision in terms of what relationships to explore in your data, so that you don't just assess relationships for the sake of just finding a p-value. I'm going to use something which is very topical, which I came across very recently. For those of you who are not from South Africa, we're currently experiencing power outages, something which is called load shedding. And recently we were told that, in fact, even today, we heard that it is being ramped up to stage six load shedding. And over the past week, we were told that the reason for ramping up load shedding to stage 6 was as a result of an unplanned strike by workers at Eskom. Now, one of the things that usually happens when people go on strike, people one of the things that happened, in fact, in this particular instance, people looked at the salaries of Eskom workers, and they were asking questions, about the demands that the workers are making. And so there was a tweet by a particular journalist who she was quoting an article from another magazine, where they were quoting that Eskom employees are the third highest have the third highest average salary in South Africa. Now that's an interesting number. Then somebody else, it was an economist, responded to that tweet and said, we should be careful in terms of how we analyze averages, because an average does not really give a clear picture of what the overall, the clear picture of the salaries in a particular environment. And as stated here, that, sometimes you can have high paid workers which can skew the distribution of the salaries. And that's what, in fact, salaries are one of the most skewed, have got skewed distribution. You understand what I mean by that. So just as a quiz, another quiz, to just test your knowledge, what do you think is the best way or an informative way of summarizing employees from Eskom? And this just is a way that helps us to get into ways of summarizing data. So I'm going to give you a few seconds to answer this question. So we're going to close the poll now in a few seconds. So let's close the poll and show the results. Interesting. So we've got 42 participants who have responded and have given a response. So what would be an informative way of summarizing salaries of employees from Eskom? An average is sufficient. A form of average and a sense of how the data are spread around the average. And we've got 17% who responded, there's no right or wrong way. It depends on how the salaries are distributed. So that's very, very interesting because, so what are the key, we can close the poll results, thank you. All right. So what are the key things that you need to present in order to make sense of data? So if you've got a bunch of numbers, how do you really make sense of those numbers? Now, two things are important in trying to make sense of data. One is a sense of location, or something called a central tendency, a measure of central tendency of the data. And that is either a mean or a median or a mode. And you're also interested in the spread of the data. So how far are the data spread from your central measure? You can either use something called a standard deviation, or you can use something called a range. You can use something called an interquartile range. And it's also important to explore your data using plots. And there are several ways of plotting your data. You can use things like your histograms, and you'll be able to obtain your mean and your variance, which are important to summarize your data. And this type of distribution that we're showing here is something which is called the normal distribution, where you've got a bell-shaped curve and where there's symmetry. And one of the characteristics of this type of distribution is that the mean and the median are equal. So one of the easiest ways to test whether your data are normally distributed is to see whether there's a difference between the mean and the median. And if it's, it's not the only test, there are many other tests, and we're not going to go through those tests. But if you look at your mean and your median and you find that they are similar, then you're more likely to have a normal distribution. However, you don't always have a normal distribution. You sometimes have data which are skewed. And here, the different types of skew can either be positively skewed or it can be negatively skewed. Salary usually takes this type of skew, which is a positive skew, where you've got a lot of people in the lower earnings, and you've got fewer people in the higher earning bracket. And here, depending, for example, this is a negative skew where the long tail is to the left. Certain conditions, for example, are more prevalent among, I'm talking about diseases, are more prevalent, for example, among the older ages. And this is where you're likely to find this type of a distribution. And here, these are some of the characteristics where it shows clearly that in a skewed distribution, your mean and your mode and your median will not necessarily be equal, and there will be at different positions depending on whether your data are left skewed or positively skewed or negatively skewed. And just to explain what the mean and the median and the mode are. So your mode is the most common number, if, in a list of numbers. Your median, if you order your numbers in ascending order, the number which is in the middle of that list, that will be your median. Whereas a mean, you add up all your numbers. If you've got 10 numbers, you add them up and you divide them by the number of units that you have. So if you've got 10, you will divide by 10. That's how you obtain your mean. So that's a difference, just in terms of explanation, what the difference is between those. All right. There are also other plots, different types of plots that you can use to assess your data, such as the box and whisker plots, which can also give you insight in terms of the distribution, whether there's the skewness in your data. And here you're also able to obtain other measures of spread, such as your interquartile range. You're able to get, so from quartile 1 to quartile 3, you're able to get the range where 50% of the data lie. And this is also helpful to identify outliers in your data. So this is one of the useful plots that you can apply. Now, the question may come is as to which type of summary do you apply in your data? And that really depends on the type of data that you have. There are different types of data, quantitative data, numerical data, and non-numerical data. And in dealing with non-numerical data, obviously we have ways of coding them so that we can deal with them numerically. So when you're looking at categorical data, for example, and you will see examples of what those are, what categorical data are. So an example of that, for example, would be ethnicity, where you're looking at different ethnic groups in a particular area, for example, in South Africa, or you're looking at different locations. You're looking at, let's say you've got 3 or more locations. Those will be categorical. And you've got also other types of data. So these are different types of variables that you can come across. You've got continuous variables, and these are variables that can take any form or any value in a particular scale. So something like your height, your weight, you can take any value in a particular scale. So those are continuous data. And then you've got count data, for example, where you're counting the number of people. You've got ordinal data, which are data, for example, they are close to categorical data, but they have got some form of a hierarchy. For example, your Likert scale, where you're able to rate from, agree, disagree, highly disagree, or something like that. Or for example, you're looking at your BMI, which is categorized. You're looking at normal, overweight, obese. That gives you an ordinal scale, or it can be severity of disease from minor to moderate to severe. That's an example of an ordinal scale. Whereas a categorical scale does not have any form of hierarchy. There's nothing that says that people in area A are different from are superior from area B or area C in any way. So, or if you're looking at eye color, if you're looking at ethnicity, those are your types of categorical data. And you look nominal data at data which give 2 options, like for example, urban or rural, or yes and no. And here on the far right, you can see the different ways in which you can summarize these types of data. For continuous data, you can use medians and your means or your mode. And that depends on the type of distribution that you found when you're exploring your data. So as we were saying earlier, one of the most important things to do when you encounter data, you need to explore it using your plots, so that that will help you to determine whether you're going to use your median or you're going to use your mode. So if your data are normally distributed, you're going to use your mean and your standard deviation. But if your data are not normally distributed, you're most likely going to use your median and other forms of indicating the spread of the data. Now, I gave these examples in terms of what the different types of data are. So, for example, blood glucose measurement is a continuous data, height, urea clearance, age. You can have salaries there and things like that. And the other examples I've already given: categorical data, site of malignancy, whatever area it can be in a medical setting. Ethnicity, if you're looking at the social determinants of disease or something like that. Binary, yes or no, or rural or urban. Now, we're going to, as we go towards the end of this part, we're going to explore some examples in terms of some data that we can look at. And one of the examples that we can use is a data set which you find in the programs data. I don't know how many of you are familiar with data. So this is what data looks like. We're not going to go into details in terms of explaining data. We'll provide you with links and resources where you can go and learn more about data. But please just indicate to me. I'm just going to have a look at the chat just to see if you can see my screen. I'm just going to see if anybody can indicate to me that you're able to see my screen. Okay, great. Thank you so much. All right. All right. So this is what data looks like. And I'm going to use this data set just to give us insight and, to see examples of the different types of data. And we're going to do a quick poll just to measure your learning. So this is how you can access this data set. This data set is called Auto and is just a data set of cars in the United States. So I'm going to call this data set. And as you can see here in the variable view, you can see the variables that are available in this data set. We've got, and here, well, all right, so in this results window, we'll see the results that are going to be, that we're going to come up with. So one of the things, for example, that you want to do when you come across a data set like this is just to look at the data. Now, what you can see here is, different types of numbers. You can also see some words. You can also see different colors. You've got black color, you've got a blue color, and you've got a red color. And this just indicates the type of variables that your data are taking, the type the type that your variables are taking up in this data set. You've got a string variable, which is highlighted in red, and you've got a string variable which has been converted into something numeric, which has been converted in blue, and all your numeric variables are in black. So just as an example, I'm going to do a quick example of one of the plots that you would like to do, and I will use, for example, this variable weight here, and it's hopefully going to show us. It shows us a chart which shows us the distribution of histogram which shows us the distribution of the variable weight. This is the weight of the car in this example data set. Now I'm just going to have show you this variable so that you can just have a look at them, before I ask some of the questions that I'm going to ask. So I'm going to give you a few seconds to look at this data. And there's something else that I'm going to come back with here in terms of the first hack that we're going to do today is about how to handle this type of data, which is string data in your data set. It is important, this data you cannot really apply it in statistical analysis. So you need to convert it into a numeric form. And we're going to show you how to do that in this example. So I'm going to go back to the presentation now, hoping that you've seen this data. And if you've got data where you are, you can have a look by at the data by just typing sys use auto, and it will bring up this data set. So coming back to the presentation. Now, like I said, one of the first hacks for today is about converting categorical variables to a factor variable, which is something that is useful when you're doing statistical analysis. You cannot perform some analysis, like for example, your chi-squared or your regression analysis with a string variable. So it's important that you convert them to a factor. And here I've given you ideas of how you can do that in Stata. I'm not going to show you the example of R. This is an example this is how you can do it, for example, in R. Maybe let me just show you how to do that with, let's just do that as an example in our data set. So if I go and code, and it is make, I need to generate a new variable, and I'm going to call it make1. And then we'll see what make1 looks like. So you can see here that make is a string variable and it is colored red. But when you come to the new variable, which is make1, it is now colored blue, which means that it is now in a numeric format. And one of the ways that you can explore you can use to explore what data types you have in your data set. You can use in Stata I forgot the command. What is it? Okay, describe. There we go. I just misspelled it there. All right, so you can see here, the original variable was a string variable, the type in which it's stored, but now it is in a more numeric format. So I'm going to go back to the presentation now. You can do the same thing in R using the structure function and in bracket your data frame, and it will show you something similar to what you saw in Stata. Now let's do our quiz. We saw the different types of variables. Maybe let me while the quiz is showing, if you're able to show the quiz now while I'm showing the data types, the data variables, can you please show the quiz? Is the quiz not showing? It's up. Okay, maybe I'm not able to see it. All right, I'm gonna give you a few seconds. I'm just gonna check in the chat to see it is showing. Okay, thank you so much. I'm gonna give you a few seconds to answer the quiz. There's 3 quizzes. So there's, we're dealing with 1 quiz for now. So I'm gonna close and go back to the question. All right. So the quiz was, what type of variable is make? Can we show the answers? So we've got some people who say 15% say that it is continuous. Some say it's ordinal. Some say, majority say it's categorical, and some say it's nominal. I'm going to explain. Maybe let's do this the fourth and the fifth quiz in succession. Let's do the fourth one and see the numbers. I'm going to show again. I'm going to show. So we're looking at the variable foreign, and this is the variable foreign here. So maybe to help you with this answer, with this question, let me do a tabulation of this variable so that you can see how many options you've got. So these are the options that you have in foreign. Maybe let me do the same thing with make. I know I'm doing it retrospectively, but that's what it is. It's got many options, but you've got only 2 options for foreign. I'm going to close the quiz now. So can we show the results? And the majority say that it is nominal, and you've got others which say that it is categorical. Okay, let's do the last one. Can we do the last quiz? So going back to the data set. So this is the variable weight that we're talking about. So I'm going to give you a few seconds, and then we can close the quiz. Can you close the quiz? All right, can you show the results? All right, by far the majority say that it is continuous, and that is correct. Some say that it is ordinal, some say that it's categorical, nominal. So as you can see, I mean, if you look at the, let's go back to the data set. Oh, okay, I need to quickly close so that I can give over to Glory. I mean, if you look at weight, weight is taking is a decimal variable, and is taking. I mean, this can take any value in a particular range. So it is definitely a continuous variable. The foreign had 2 options. So it is a binary or a nominal variable, whereas make is a categorical variable. So I'm going to move very quickly now to try and move to the end. We can close the quiz. So really, so what Gloria is going to be talking to is really about inferential how to make inferences about from a sample about a population. We can't measure. Sometimes we're interested. I mean, we're always interested in making statements about a population, but we can't measure the population because it's too hard, it's too large, and it is very expensive. So we draw out a sample to try and find a sample that will be representative of the population, so that we can make statements about that particular population. I'm going to skip quite a lot of this because I believe that Gloria is going to cover some of these things. So I'm going to skip these areas and maybe just come to this. This is the second last slide. Now, here I just want to introduce to you a concept, a particular concept. Like I said earlier, so we're going to be talking about p-values like I said earlier, one of the things that a lot of people ask when they approach someone who's a statistician or who applies statistics is how they can obtain a p-value. Now, a p-value can tell you something about statistical significance, but one of the important questions is about whether that statistical significance tells you anything about something which is relevant clinically or in a public health setting. And this is an example of something that a student of mine, an examiner for a student of mine wrote when she was examining the student. And she says, for the second objective results, given that small for gestational age and large for gestational age are two extremes, how significant is the finding that they were statistically significant? So she found that there were differences in fat mass between small for gestational age and large for gestational age children. In fact, the two were different from appropriate for gestational age. And the examiner wanted to find the clinical relevance of this finding. So I'm really bringing up this point to show you that sometimes it's not enough to look for statistical significance. You must also try and ask yourselves the question: what is the significance of this number in practical terms? Is this a clinically relevant difference, or is this a difference which can make an impact from a public health perspective? Not all relationships, are meaningful. You can have something which is statistically significant. This is just an example of relationships which may be statistically significant, because you can see that, for example, if you're looking at bedsheet tangling and cheese consumption here, cheese consumption is, there's a relationship. If looking at margarine consumed and divorce rate, I think this is a clear example, the second one. Margarine consumed and divorce rate, they sort of follow each other. The trends follow each other. So are you going to say here that consumption of margarine is related somehow to divorce rate? That would be a very easy thing. That if it were the case, it would really make life very easy to prevent divorces. You either stop taking margarine or you eat a lot of margarine, depending on the type of relationship. So this is where I'm going to end it for now, so that I can hand over to Glory, who will then do the second part of our presentation. Over to you, Glory.
So statistics broadly involves the collection, organization, and interpretation of data. And there are two basic types of statistics broadly. Firstly, we have descriptive statistics, and second, we have inferential statistics, or what others also call analytical statistics. So in descriptive statistics, we are more concerned with describing the characteristics of our population. And we usually use measures of central tendencies like invariability, like what Lukanya was highlighting. We may also use charts, graphs, tables, etc. And in inferential statistics, we are more concerned with making estimations of population parameters. For instance, in the example that he was giving of weight, we might want to know, so then what is the average weight in our population? So that's point estimation. Or we might be interested in explaining the relationships that exist between variables. And the results are usually shown with the help of probability scores. All right. So p-value, what is it? So p is the probability. So the formal definition is that a p-value is the probability of obtaining a result equal to or more extreme than what we observe in our data. And the founder of this is Carl Pearson. I think most of us are familiar with what we call the chi-square now. And the smaller the p-value, the larger the significance, because it tells us as investigators that the hypothesis under investigation may not adequately explain what we observe. So we've covered this quiz, and we've said if a p-value is less than 0.05, what it actually means is that if there truly was no effect, then one would expect to see a result like this less than 5% of the time. In other words, the occurrence is not by chance. So a p-value can be loosely defined in other literature as the probability that the observed relationship is due to chance. So then if the p-value is way less, then we know it's not by chance. And as we might all know, the cutoff for p-value is set at 5% most of the time. This is not a standard, but most of the time, there are some instances where we can talk about penalization and all, but it's not covered in this session. So then if the p-value is less than 0.05, we say it's statistically significant, and we therefore reject the null hypothesis. I'll talk about the null hypothesis and the H1 or the alternative in a bit. And if it's greater or equal to 0.05, then we fail to reject H0. And then testing potential harmful interventions, alpha, or the significance level is set at 0.05 or 5%. What we are showing here are the general steps that are involved when we're doing significance testing. So the first question is to state your research question and then determine the probability of erroneous conclusions, which is usually 5%. And then you choose your test, your statistical test, or calculate the test statistics. You get your p-value, you conclude, and you infer, then have your formal conclusion. All right, so in stating the research question, I think this is pretty straightforward and common to most of us. So the idea is to assume the status quo or the state of affairs in two treatment groups. For instance, is the mean hemoglobin in urban and rural children the same, or they are different? So under the null hypothesis, these are the assumption or the status quo. We assume no change, we assume that there is no relationship, or we assume that the two populations being compared to are not different. In other words, they're the same. Under the alternative hypothesis, or what we call H1 or HA, we assume that the two groups given are different, or there is some relationship that exists between the given variables, or there is a change that occurs, etc. So in other words, the status quo things remain as they are, and there are no relationships. Whereas the alternative assumes that there might be other relationship. And we assume that the status quo or the null hypothesis is always true until we get enough evidence against it, which would be the probability being less than 0.05 or 5%. I'll bring to our attention what we normally call type 1 error and type 2 error. So as a researcher, if you accept H0 And in reality, the H naught is true, that's a right decision. And the same applies for the alternative. However, there are instances where you might then decide to you might decide to reject H naught when in actual fact, in reality, H naught is not true. That would be type 1 error. Or type 2 error where you fail to reject H naught, in other words, you accept H naught, but H1, the differences actually exist. So in other words, you fail to detect the differences. That would be type 2 error. So in type 1, like we've said, you state that there's a difference when in fact there is no difference between the two groups. And this is also called alpha, the probability alpha, type 1 error. And it's usually set again at 0.05. And in type 2, there are no differences. You state that there are no differences when in actually there is. In other words, you miss an existing difference. So basically, when you miss a true difference that exists between drugs, for instance, you're introducing a new drug, there's a missed opportunity for an introduction for, let's say, a drug that's more cost effective, just as an example. So I see we have only 4 minutes left. So then the next step would be to determine your test statistic, which is calculated as shown there. I'm not going to go into details with that. And then you infer based on the value that you get. Those were the steps, and then your conclusions. What I want us to get to, which I think is the core or the main message from this presentation. Statistical significance does not necessarily mean real significance. And lack of statistical significance, on the other hand, also does not necessarily mean that the assertion or the status quo or the H naught is true. And this is largely affected by the sample size. So if the sample size is large, you are likely to have low p-values. Whereas if the sample sizes are small in general, there could be a real difference, but you're not able to detect it. So sample size then becomes one of the most important steps that we do in statistical analysis. So before you do your your research, or be it a grant or grants application, or even if you're doing secondary data analysis, I think it's important to interrogate your sample size. And if the sample size is predetermined, it's also very important then to determine how much statistical power you have to determine the effect. And I think that should be our take-home message. Just to say, in hypothesis testing, sometimes it may be one-sided, or sometimes it may be two-sided. What we mean there is that sometimes you may just generalize and say one drug is better than the other, but in some cases, for instance, you may say this drug performs better or it performs worse than the other. I'm going to talk about the common uses of p-values, which I strongly suggest that we should avoid. So the first one is to use p-values for baseline characteristics in a randomized control trial. So and then the second is describing the strength of an effect, especially when the p-value is less than 0.05. So this table here is showing us a table. For instance, this is showing BMI, sex, age, and etc. Categorized by treatment, subjects, and placebo. So in a randomized control trials, for instance, for those that do randomized control trials, you will know that beforehand, we already do a process which we call randomization. So by randomization, the process of randomization, we assign the given treatment or the new treatment to participants, to either new treatment or the control, which is the standard of care, randomly during that process. That's what it's trying to achieve. So then after that, there is no need to do a p-value, for the reason that if we know that the randomization worked, so there is no need to then assess whether a given characteristics is by chance, because these participants are already distributed to be the same. We know that the randomization worked. So then that's one instance. And then the second instance that I want us to get into, I would encourage all of us to read this paper known as the stroke explanation and elaboration. So I just took a snapshot there. If you check the other chapter, it should be 13, that talks about descriptive statistics. So it's highly discouraged to report p-values when you are presenting your table 1 usually, which is your descriptive table. And this is for a number of reasons, and I will state just 3. The first reason is when you are doing your descriptive statistics, your research question is not to see whether there are statistical significance. Remember, when we defined our descriptive statistics, you are just showing us what the data has. So the first reason is that that's not our research question. The second one is that when you are doing descriptive statistics, you will run into an issue that is known as multiple testing, because you will test whatever is on your outcome variable against each of the variables several times, and that is known as multiple testing. And when you do that, you are supposed to correct for that multiple testing using other penalizations, for instance, the Ben-Feronik correction, etc. So then normally we don't do this because of that problem of multiple testing that we do not correct for. And then the last reason is that you are likely to see false positives in your data set. So just to conclude, and then I give it to Lucanio. P-values cannot confirm whether the researcher's argument is correct or not. And being less than 0.05 cannot ensure that the researcher's arguments are true. And there is a belief, which is erroneous, that scientific validity can lead to considerable distortion in decision making. So the recommendation is that inference should always be based not only on p-values, but we also need to consider other contextual factors.